Blackbody radiation is the electromagnetic radiation emitted by an object solely because of its temperature. A blackbody is an ideal object that absorbs all incoming light and energy without reflecting any of it. Although a perfect blackbody does not truly exist in nature, many everyday objects behave similarly. For example, heated metal in a stove, the filament in a light bulb, and even the sun emit radiation that closely resembles blackbody radiation. As an object becomes hotter, it not only emits more radiation, but also changes color. A piece of metal heated in a furnace may first glow dull red, then orange, yellow, and eventually white as its temperature increases. This change occurs because hotter objects emit light with shorter wavelengths and higher energies. Blackbody radiation therefore provides a direct connection between temperature and the color of emitted light. The study of blackbody radiation played a major role in the development of modern physics and quantum theory. In the late 19th century, classical physics could not accurately explain the observed distribution of radiation emitted by hot objects, especially at very short wavelengths. To solve this problem, Max Planck proposed that energy is emitted in tiny discrete packets called quanta. This revolutionary idea became the foundation of quantum mechanics. Today, blackbody radiation is important in many scientific fields. Astronomers use it to estimate the surface temperatures of stars. Engineers apply it in thermal imaging and infrared technology. And climate scientists study Earth's radiation balance to better understand global warming. Even though the concept originated in physics, blackbody radiation has practical applications that affect technology, medicine, environmental science, and our understanding of the universe. This slide explains how the color of a flame is related to energy, temperature, and electromagnetic radiation. An electromagnetic spectrum is shown here, including gamma rays, X-rays, ultraviolet light, visible light, infrared radiation, microwaves, and radio waves. Visible light occupies only a small portion of the entire spectrum, yet it is the range our eyes can detect. The visible region consists of different colors that correspond to different wavelengths and energies. Violet and blue light have shorter wavelengths, higher frequencies, and higher energies, while red light has longer wavelengths, lower frequencies, and lower energies. This implies that wavelengths decreases as frequency increases. Because energy is directly proportional to frequency, blue light carries more energy than red light. Now let us connect this concept to the color of flames. When a substance is heated, its atoms and molecules gain thermal energy. As the temperature increases, the particles emit electromagnetic radiation in the form of light and heat. The color of the emitted light depends strongly on temperature. Cooler flames typically appear red or orange because they emit lower energy light with longer wavelengths. As the temperature rises, the flame color shifts toward yellow, white, and eventually blue, which corresponds to shorter wavelengths and higher energies. This is why a blue flame, such as a flame from a laboratory Bunsen burner or a gas stove with sufficient oxygen, is generally hotter than yellow or orange flame. The blue flame indicates more complete combustion and higher thermal energy. The heated metal shown here demonstrates the same principle. As metal becomes hotter, it begins to glow red, then orange, and eventually white as the temperature continues to increase. This phenomenon is a form of blackbody radiation, where hot objects emit light due to their temperature. Blacksmiths and metal workers have historically estimated the temperature of heated metals simply by observing their color. Similarly, astronomers estimate the temperatures of stars based on their emitted colors. Red stars are generally cooler, while blue stars are much hotter. The images of the different flames on the slide visually demonstrate the relationship between color and energy. The red flame represents lower energy radiation, while the blue flame represents higher energy radiation. This concept is important not only in chemistry and physics, but also in everyday applications. Gas stoves, welding torches, fireworks, and even candle flames all display colors that provide information about temperature, energy, and the chemical processes occurring during combustion. Overall, the color of a flame serves as a visible indicator of the energy and temperature of the emitting substance. This slide gives us a perfect look at a concept called blackbody radiation, which is just a fancy physics term for the way every single object in the universe constantly glows with light based entirely on its temperature. Even though we can't see this light with our own eyes, anything with a temperature emits it. And for living creatures, that light falls into the infrared spectrum, which we experience as heat. By looking at the color scale on the right, which runs from a cool 50 degrees Fahrenheit up to a warm 100 degrees Fahrenheit, we can see how this works in the animal kingdom. On the left, the meerkats are warm-blooded, meaning they generate their own internal body heat. Because they are much warmer, they emit infrared light that shows up as a bright yellow. On the right, the alligator is cold-blooded, meaning its body temperature matches the chilly environment around it. Because it is much cooler, it emits less energetic infrared light, causing it to blend into the background as a darker, muted orange. Special thermal cameras are able to capture this invisible heat-based light and translate it into the colorful images we see here, essentially letting us see temperature as a visual map. Building directly on how we saw animals glow in the dark, this slide shows how the military uses that exact same concept of blackbody radiation to gain a massive advantage on the battlefield through night vision and thermal optics. Remember, because humans are warm-blooded, our bodies constantly emit a steady stream of invisible, heat-based infrared light into the surrounding environment. In pitch-black conditions, where the human eye can see absolutely nothing, a soldier wearing the specialized thermal gear shown in the top image can easily spot human targets. As you can see in the larger aerial drone or scope footage below, the cold ground, trees, and rocks appear as dark, muted shades of gray because they aren't radiating much heat. However, the enemy combatants stand out like bright, glowing white beacons against the darkness because their high body temperatures cause them to emit much more intense infrared radiation than their chilly surroundings. By utilizing technology that captures this naturally occurring blackbody radiation, forces can strip away the cover of darkness entirely, turning an enemy's own inescapable body heat into a visual tracker that makes it impossible to hide. Now that we have seen how animals and humans give off invisible heat signatures, let's look at the formal physics definition of what is actually happening. Blackbody radiation. In physics, a blackbody is an idealized perfect object that absorbs 100% of any light or radiation that hits it, reflecting absolutely nothing back, which is why the sphere on the left appears perfectly black. However, because it absorbs all of this energy, it must also release energy, and it does so by emitting radiation in a very specific pattern that depends entirely on its temperature. To understand how temperature changes this glow, let's look at the three stars on the right, which act like massive cosmic blackbodies. The graph lines show the intensity or brightness of the different colors of light each star emits. At a relatively cool cosmic temperature of 2500 Kelvin or 2227 degrees Celsius, the first star peaks deep in the infrared region, spilling just a little bit into the visible spectrum and making the star glow a dull, warm red. When we increase the temperature to a scorching 5800 Kelvin or 5527 degrees Celsius, which is roughly the surface temperature of our sun, the peak of the curve shifts into the middle of the visible spectrum, causing the star to blast out a bright, balanced yellowish-white light. Finally, if we raise the temperature to an unimaginable 18,000 Kelvin or 17,727 degrees Celsius, the peak shifts beyond the visible spectrum into high-energy, invisible ultraviolet region. Because it is leaking heavily into the blue and violet side of the spectrum, the star appears to us as a brilliant blue star. Ultimately, this slide demonstrates the central principle of blackbody radiation. As an object gets hotter, it not only becomes brighter, but the color of its peak emission also shifts from cooler reds to warmer whites, and finally to intense blues. Wien's displacement law is the mathematical rule behind why those glowing stars change color. The colorful spheres on the left side of the slide perfectly track this journey. We start with a cold, non-reflecting blackbody sphere, which heats up to a dull red, then a bright yellow, and finally a brilliant cosmic blue. The graph on the right illustrates how the peak wavelength progresses to shorter wavelengths as blackbody gets hotter. Don't let the equation at the top scare you. It represents a very simple, intuitive concept. An object's temperature and its peak glowing wavelengths are inversely related. In plain terms, as an object gets hotter, the wavelength of its light gets shorter and more compressed. Think of a guitar string. Plucking a tight, high-energy string creates short, rapid vibrations, while a loose string creates long, slow ones. Light works similarly. If we look at the main graph, the horizontal axis shows the wavelength of light in nanometers, where longer waves on the right represent lower-energy infrared light, and shorter waves on the left move through the visible rainbow towards high-energy blue and violet light. Look at the lowest curve on the graph at 3000 Kelvin. Its peak wavelength is way out to the right at 966 nanometers, meaning it mostly glows in invisible infrared heat, spilling just enough into the visible spectrum to make the object look dull red. As the temperature climbs to 4000 Kelvin and 5000 Kelvin, notice how the crest of the hill physically displaces or slides to the left. At 5000 Kelvin, the peak hits 580 nanometers, right in the yellow-green zone of our visible rainbow. When the object reaches a blazing 6000 Kelvin, the peak squeezes down to a short 483 nanometers, placing the absolute brightest part of its light right in the blue-violet region. Wien's displacement law is the exact tool astronomers use to look at a distant star through a telescope, measure the color wavelengths of its brightest light, and instantly calculate exactly how hot that star is without ever having to visit it. An important real-world application of blackbody radiation is estimating the surface temperature of stars. In astronomy, stars are often treated as approximate blackbodies because they absorb and emit radiation in a predictable way based on their temperature. The graph on the right shows the intensity of electromagnetic radiation emitted by the sun as a function of wavelength. Notice that the curve reaches its maximum intensity at a wavelength of approximately 500 nanometers, or 5.00 times 10 to the minus 7 meters, which lies in the visible region of the electromagnetic spectrum. This explains why sunlight appears brightest in visible light and why the human eyes are most sensitive in this region. The graph also indicates that about 9% of the sun's radiation is emitted in the ultraviolet region, about 40% in visible light, and about 51% in the infrared region. Therefore, the sun emits energy across a broad range of wavelengths, but the peak wavelength is the most important quantity for determining temperature using Wien's displacement law. Wien's displacement law states that the wavelength of maximum emission multiplied by the absolute temperature equals a constant value, which is 2.898 times 10 to the minus 3 meters Kelvin. From the graph, the maximum wavelength is approximately 500 nanometers, which must first be converted into meters, 5.00 times 10 to the minus 7 meters. Rearranging the equation to solve for temperature gives this equation. Substituting lambda max produces a temperature of 5.796 times 10 to the third power Kelvin, or 5,796 Kelvin. Note that absolute temperature in Kelvin is simply equal to the temperature in degrees Celsius plus 273.15. Plugging in the surface temperature of the sun that we just calculated gives approximately 5,523 degrees Celsius. This value is remarkably close to the accepted surface temperature of the sun. This example beautifully illustrates how the color and wavelength distribution of emitted radiation are directly related to temperature. By simply analyzing the light emitted from distant stars, scientists can estimate their temperatures without ever physically traveling to them. Now, let's try an online activity to reinforce our understanding of blackbody radiation. Log in to the course site on D2L. Click the Content tab at the top. In the left menu, open Lecture Material, then select the module titled 20 Blackbody Radiation. Under that module, find Lab 20 Blackbody Radiation and download the lab worksheet. Complete it as you work through the online simulation. Return to D2L and under the same module, open Simulation, Blackbody Radiation. On the simulation page, check Graph Values, Labels, and Intensity from the menu. Move the triangular arrow on the blackbody temperature gauge on the right to Earth, light bulb, sun, and Sirius, progressively observing how the emission curve or spectra changes. If the peak in the spectra is too weak or too intense, you may rescale it by tapping the zoom in and zoom out icons in the top left and bottom right corners of the simulation page. Sketch the spectra and fill in the blank boxes in the table on the lab worksheet. Record the reference temperature of the bulb and celestial bodies shown on the right. Click and drag the cursor point on the curve to place it at the peak and record the maximum wavelengths of emitted light. Be aware that the unit for the wavelengths here is micrometers, which is 10 to the negative 6 meters. Use Wien's displacement law to calculate the temperatures of the bulb and celestial bodies. Show your work in a clear and logical manner with correct units in the lab worksheet. Sketch the spectra in the lab worksheet. Indicate lambda max on each spectrum.